Okay, good evening, students. We are discussing our practice paper 12 today. So, in this paper, you have mainly the questions from Unit 2, bonding and structure. Okay, in our theory class, we have completed some topics of the lesson. For example, we know how to draw Lewis structures, then we know how to get the electron pair geometry and shape of a given molecule or ion. And then in the last week, we discussed about the hybridization of the central atom. Okay, so like that we know some of the theories. Okay, there are things to still to complete in the lesson, but however, from the things we learn, let's do some questions and just kind of revise those points again. In the next week also, you will be having a similar paper. Okay, in your next physical class, I'll give you this paper, paper 12 and paper 13 together. Okay, right, I'll show you the paper. So this is what we are going to discuss now. Okay, right, look at the first question. It's asking, what is the incorrect Lewis structure?
So I got few answers, right? So I'm just asking to check. Yeah, answer is answer 4. Fourth one is the wrong one. Good. Okay. Fourth one is the wrong one. Why the fourth one is incorrect? That's what we need to write in our discussion. Okay. So if I take the fourth structure, it is like this. F N double bond O double bond O. Right? So in the given structure, the nitrogen has made how many bonds? It has made 5 bonds. It is made 5 bonds. But that is not possible. We know why. Because nitrogen must follow a thing called octet rule. So what is this octet rule? Octet rule means, okay, octet rule means oct means 8. 8. The rule of 8, right? So normally any given central atom should try to complete its octet. Okay. So what is the purpose of making bonds? That's the theory part actually coming. So why atoms and elements are making bonds? We have to think about that to understand the octet. Okay. So the reason is this. So when let's say nitrogen atom, for example, if you take nitrogen atom, its electronic configuration is 1s2, 2s2, and 2p3. So you have only 5 electrons in the valence shell. So for nitrogen, this configuration is not that stable. Okay, so it has a certain stability, but nitrogen likes to be more stable. Okay, for that means it has to complete its second energy level. To complete the second energy level, it needs to complete the P sub energy level. So normally, P sub energy level, if it is stable, it keeps 6 electrons in the P sub energy level. So that means you need 3 more electrons to do that. Okay, so that's how nitrogen fills the 8 electrons. So why this configuration is so important? Because that is the configuration what noble gases can. So we call it as noble gas configuration. Noble gas configuration. So that is the stable configuration. Nitrogen try to achieve that state. For that, okay, it has to take 3 more electrons. Understood? So like that, octet rule is, okay, normally elements are making bonds to complete its octet. Okay, so oxygen make 2 bonds. Okay, to complete the octet, because oxygen needs 2 more electrons. Just remind the O-level theory, right? So carbon in the valence shell, it has 4 electrons, right? So then carbon needs to make another 4 bonds, right? To get another 4 electrons. Understand? So that's how elements, those P-block elements are achieving the stable configuration. So purpose of making bonds is actually to attain a noble gas, or we say stable electronic configuration. So these nitrogen, carbon, oxygen, those elements. Okay, so there are several elements here. Phosphorus, they all achieve the noble gas configuration by completing its octet. Understand? So that is what we call as octet rule, right? Octet rule. So here, our nitrogen, okay, our nitrogen must follow octet rule. So that means nitrogen can't keep more than or less than 8 electrons. You understand? Nitrogen must keep 8 electrons, no more, no less. Okay, but in this structure, it has made 5 bonds. That means in the nitrogen valence shell, there are there are 10 electrons because 5 bonds means 10 electrons. So that is not possible. This one is not possible. Not possible. Okay, because why? Because carbon, nitrogen, oxygen, chlorine must follow octet rule. Must follow octet rule. So they can't keep more than or less than 8 electrons. Understand? So therefore, this structure is not existing. It is wrong. It is wrong. So it's not possible. Understand? Not possible. Because why? Because in the second energy level, why they must follow the octet rule? We have to write a reason for that also. Like I mentioned here, okay? So nitrogen and other elements, they like to keep their 8 electrons. No? For example, take several elements, carbon, nitrogen, oxygen, chlorine. Okay, these elements are in the second period. So take third period elements also to extend the third period. So just beneath the carbon, you have silicon. Under the nitrogen, you have phosphorus, sulfur, chlorine, like that. Okay. So in the second energy level, what is the maximum electron holding capacity? Maximum 8 electrons can fit. Okay, in the second energy level, you can't keep more than 8 electrons. You remember, in the first energy level, you have 2 electrons maximum. Okay, second energy level, 8 electrons. Third energy level, you can keep 18 electrons. Like that, you have a maximum limit. Understood? So second energy level, you can't keep more than 8 electrons. That's why CNO must follow octet. Understand? They must follow the octet. Now take the compound phosphorus. The same thing is made with phosphorus. Did you notice? In the fifth answer, in the phosphorus, it is not wrong because phosphorus can keep 10 electrons. You can see phosphorus is a third period element. So its maximum electron holding capacity is 18. That means it can keep up to 18 electrons. Okay, so here just keeping 18, 10 electrons is no problem for the phosphorus. Okay, so phosphorus can overcome the octet. Okay, so first of all, we should try to give the octet. So it's possible, right? It will overcome the octet because it can keep more than 8 electrons. So this is a good MCQ. Easy, I know, but there is some deep theory is there. Okay, I hope you all understood that. So what is the theory? Octet rule. So nitrogen, the fourth answer, is the wrong one, right? But the similar one is there for the fifth answer with the phosphorus, but that is not wrong. This is a correct structure. Okay, so write a good review why this one is wrong and tell about the octet rule. Okay, tell about the octet rule and tell this point also CNO must follow octet, right? And then tell it is not applicable for the phosphorus or other, right? So phosphorus can keep more than 8 electrons, it means. Okay, right. So here you can write why it must follow the octet rule. You can say in second energy level, we cannot keep more than 8 electrons. In second energy level, we cannot keep more than 8 electrons. That is the reason. Understood, Lamai? So any problem on this one? The other structures are correct, okay? Other structures are correct. If I take the first one, carbon dioxide. This is a kind of a Lewis structure that we can draw for the carbon dioxide. So you can see charges are there, okay? So this is, therefore this is unstable, but a Lewis structure. So this is the carbon dioxide, another Lewis structure. So carbon dioxide, this is the normal structure we draw on of this, and we can draw this also, right? This is a stable one. This is an unstable one. Okay. Right. And then HCN is there. That is a correct one. Look at the third one. Third one also we can note something there. This BF2. BF2, boron. Boron, now you can see here octet is not completed. Octet is not complete. Octet is not complete. So it is okay with boron. Oh, sorry, beryllium. Okay, this is beryllium. So boron, beryllium, they can keep less than 8 electrons. Okay, because they are metals, no? They are not that electronegative. So they are not trying to make they are complete octet, so they don't need, right? So they just try to make some bonds and they achieve octet in some other way. We will be discussing it later. So just know there are compounds like, BeCl2, okay, and BF3. There are compounds like this. They are electron deficit. Electron octet is not completed. So write a full review. I mean, the question is easy, I know, but just write something which will, give you a very good clarity about the lesson. Okay, right. So, any questions on the first MCQ? Anything to ask? Okay, now let's go to the next MCQ. So, tell me what is the answer you got for the next one. So, after getting the Lewis structure, I'll draw some Lewis structures with you when we discuss the third MCQ. Right? So after getting the Lewis structure, our next theory topic we discussed is about the electron pair geometry and the shape of that molecule. So in the given compound here, it has 3 central atoms. Actually, it has 3 central nitrogen atoms. Okay. So for them, we have to find separately their electron pair geometry and the shape around the central atom. Okay. So what is the theory we use for that one? It has like 5 letters. VSCPR theory. Okay. VSCPR. I'll remind you a little bit regarding the VSCPR theory. Okay. So what is this VSCPR theory? VSCPR. Okay. So the long name of the theory actually tells you what is happening. V stands for valence. Valence shell. Yes. Electron pair. Valence shell, electron pair, repulsion theory. Repulsion theory. So that means what? It tells you everything. The electron pairs in the valence shell are repelling from each other. The electron pairs in the valence shell are repelling from each other. Because why do they repel first of all? Because electrons are negatively charged. You know, from your O-level science, that not electrons, maybe you know that, but similar charges, the ones with similar charges are repelling from each other. Understand? So negative repel. Positive, those charges are repelling from it, right? So here, in these structures, around these central atoms, you have electron pair. You can see here. Okay. So here you have a double bond. And there you have 2 single bonds. Right here, like that. You have bonds, and then you have these lone pair souls. Right? So we call them as, so the electron pairs that are repelling from each other, we call them as repulsion units. Repulsion units. So there are 2 types of repulsion units. Okay, you have bond electron pairs and lone electron pairs, BP and LP. Okay, BP and LP. So they repel from each other. So I'll explain that one with a simple example. Let's take BeCl2. In BeCl2, around this beryllium atom, you have 2 bonds. So each bond is 2 electrons. So what do? They repel from each other. So to minimize that repulsion, they should arrange in this way with 180-degree angle. So then the repulsion will be minimal. That's the logic. Okay. So let's take BF3. Around boron, you have 3 bonds. That means 3 repulsion units. So to minimize the repulsion, they must arrange in 120-degree angle. Okay, 120-degree angle. So that's how they minimize the repulsion. Understood? So they keep a maximum distance among the repulsion units. So then it becomes more stable. If the repulsion is low, stability will be high. That's the theory. Can understand no longer, isn't it? Like that, you can easily understand. Okay, so then when you have 4 repulsion units, then the story little bit change. Okay, so if you have 4 repulsion unit, it is not going to be 90-degree angle to it. Okay, because we live in a 3-dimensional world. Okay, so we have better options than 90 degrees. So think about the 3D plane. Think about the 3D plane. So when, let's say CH4, remember we discussed this in the class. Okay, so 2 hydrogen bonds are coming, carbon hydrogen bonds are coming in front of the plane. Okay, and they keep 109.5-degree angle. It is larger angle than 90 degrees. So it's a better way of to minimize repulsion because they can make a larger distance, keep a larger distance. Okay, and then another carbon hydrogen bond will go to the backside of the, or you can say into the plane. Okay, so like that they can keep a maximum distance by coming into a 3-dimensional arrangement. Okay, not a 2-dimensional arrangement. You can see the BCl2, BeCl2, and BF3. Those are 2-dimensional arrangement. But our this pH4 arrangement is a 3-dimensional arrangement. Like that, depending on the number of repulsion units, they keep a certain arrangement. So we call it as electron pair geometry. Okay, what do we call it? Electron pair geometry. So we had to put a name for this one. So what's the name we gave for this one? So you can see it's 180-degree angle. You can see they kind of in a line, no? Straight line. So we call this one as a linear electron pair geometry. And this one is trigonal planar. Because once you connect them, it resembles a triangle. Okay. And this one is the tetrahedral electron pair geometry. Just remind the theories we learned in the class. Okay, so it resembles a tetrahedron when you connect the atom. Understand? So at the middle of the tetrahedron, you will have the carbon. Okay, so like that, when you have 5 repulsion units, you have trigonal bipyramidal electron pair geometry. When you have 6 repulsion units, you have octahedral electron pair geometry. So that is the summary about the repulsion unit. Understand? So then there are 2 points I want to highlight. Okay, first thing, when we have like let's say multiple bonds are what? You have more than one bond. Let's say you have a double bond, you have a triple bond. Okay, so then in those cases, we don't consider them as separate units. Understand? We consider them as a single unit. So now you can see in our question, you have a double bond. So double bond is it's not 2 units. Okay, even though there are 2 bonds, we call it as, we consider it as one repulsion unit. One repulsion unit. Understand why? Why do we take it in that way? Because these double bonds can't repel from each other. It's true that they are made of electrons, but those can't repel from each other. Understand? They kind of stick together. Okay, because these two, there you have 2 electrons in one bond and another 2 electrons in the other bond. That means 4 electrons. All those 4 electrons are held firmly by this N1 and N2. So they are kind of keeping the 4 electrons together. They don't allow these 4 electrons to repel from each other. Understood? So therefore, we call it, consider it as one repulsion unit. Likewise, here also you have a single repulsion unit. Understood? So around this N1, then how many repulsion units you have? Okay, how many VSE PR units we have? Okay, we have 3 VSE-PR units. Understood? Around this N2, we have, with the lone pair is also a repulsion unit. 1, 2, 3. Another 3 VSE-PR units. Okay, around this N3, you have 2 VSC-PR units. So depending on the number of VSC-PR units or repulsion, they assume the electron pair geometry. They assume the electron pair geometry. Okay, so if there are 3 repulsion units, it is trigonal planar electron pair geometry. This is also trigonal plane. And this one is linear electron pair geometry. Now check your answers. Check your answers. You have trigonal planar, linear in only one answer. So that means answer must be answer 5. Okay, so most of you selected the answer 5. Very good. Okay, very good. So that's how we decide the electron pair geometry. So that is actually one part of the question. So what is the other part of the question? It's asking the shape of the molecule also. What is shape mean? Shape mean. So this is different from the electron pair geometry. Yes, right? Electron pair geometry is telling you regarding how all the repulsion units are arranged. But you can see there are 2 types of repulsion units, no? Right? So consider the lone pair. So lone pair is only only attracted to one atom, which is this nitrogen, right? So there is no other atom attracting the lone pair. Understand? So therefore, when you just let's say when you consider the bonds or when you consider the position of their nuclei, you will not see anything here. Okay, so something like this. Now they both are trigonal plane. That means something like this. Okay? But here you have a pair of electrons on it. Understand? So it is affecting the electron pair geometry, but when we consider the shape, you will not see the lone pair. Okay, because there is no bond here. So we consider the bonds and decide the shape of this molecule. Okay. Now you can see this is trigonal plane electron pair geometry, and this must be trigonal plane shape. Shape is also trigonal plane. Understand? But here, since you have one lone pair, it is kind of disappearing from the shape. It has an effect on the shape. Okay. That's why in the first place this became trigonal plane, right? But when we decide the shape, it is kind of not considered, right? It is not there. So we consider only the bonds, right? We kind of taking an like this is kind of like taking an X-ray. You only see the bonds. So just consider what do we see? We see the nuclei of these 3 elements. That means when you connect them, you will have something like this, a bent shape, or we call it an angular shape. Understand? So here the shape and electron pair geometry both are linear. Okay, so check the 5th answer. It contains the shapes also the correct one. Trigonal plane, angular, and linear. Okay, so I hope you understand this well. Okay, because this is the second skill we develop. After we are able to draw the Lewis structure, we have to get this geometry, electron pair geometry, and the shape of the given molecule one. Okay, so you will have some considerable marks in the test from this topic. Right, so very good. You got the answers correct. Okay, well done. Answer is answer 5. Okay, now I promised you to explain the method of drawing Lewis structure. Okay, so now let's try the third MCQ. Third MCQ is a model MCQ, and then you have the fourth MCQ, which is very similar to that. Okay, it is the past paper MCQ. It is from 2024, the latest A-level paper. Right, so now let's do the third MCQ. Now, can you please tell me what is the answer you got for the third MCQ? What is the answer you got for the third MCQ? So now I'll do like this, okay? Right, I'll discuss the third question with the proper Lewis structure method. Okay, proper Lewis structure method. Right, and I will give you a short method, a short approach for the fourth MCQ. Okay, so then you have 2 MCQs, but then those are similar, but the method I'm going to teach you or explain you is different. Okay, so send your answers to the chat, and I'm discussing the answers. You can use it. So we have to draw BF4 minus, PLO3 minus, and XeOF2. These are the molecules we need to draw. Right. So what is the Lewis structure method? It first suggests me for you to get a skeleton structure. So when we get the skeleton, we place the least electronegative element, okay, at the center, and we put the other atom, more electronegative ones around that. So sometimes they give questions like this. So we have to get the skeleton by ourselves. Okay, some cases are there when there are many atoms. Okay, there are 5, 6 atoms. Okay, so then we can't decide the skeleton. So they have to give one. Understood? So here, because they are not giving a skeleton, that means the least electronegative one will be the central atom. That means simply there will be only one central atom. Okay. If they are asking you to draw a molecule like we did earlier, in the second question, they must give the skeleton. Okay, get the point? Now here, what is the central atom? Boron. So around boron, you have 4 fluorine atoms. Okay, now if we consider the method, Lewis method. So first it is asking you to get the number of valence electrons. I think you can easily get the number of valence electrons by looking at the group number. So boron is in which group? It is in group 13 according to the level symbol. Right? That which means simply it has 3 electrons in the outer shell. Take the configuration also. 1s2, 2s2, 2p1. So 2s2, 2p1 are the last energy level electrons, which means you have 3 electrons. Understand? 3 electrons. So boron is having 3 valence electrons, right? And then one fluorine atom will have 7 valence electrons in the same group because it is group 70, right? And there are 4 bromine atoms. So that means 7 into 4, you have total 28 electrons. And we can't forget the charge also. It is BF4 minus. Minus means, okay, minus means the negative charge means it is an extra electron. So why in the first place the ion became negative? Because it has an extra electron. So when we take the valence electron count, we have to consider that negative charge and add that extra electron. Okay, so if you get the sum, you will be seeing you have 32 total electrons. Fantastic. 32 total electrons, right? So from those 32 electrons, now our task is to show these 32 electrons, how they are there in the molecule. Okay, so take for example water. Water, if you consider in the same way, oxygen is having 8 electrons, hydrogen, 2 hydrogen are having 2 electrons. Total 8 electrons are there. In our Lewis structure of water, what did we do? We show that 8 electrons. Okay, 4 electrons are there as bonds, and another 4 electrons are there as lone pairs. That's the task. So like that, we are going to represent those 32 electrons in the molecule. But we have already shown some electrons. No? Look at the 4 bonds. We have already represented 8 electrons. That means 4 electrons means 4 bonds mean 8 electrons, right? So those 8 electrons we have to subtract from the total. That means we get 24 electrons. 24 electrons means if you put it into pair, 12 electron pair. 12 electron pair. So we have to place those 12 electron pair to the peripheral atom. Okay, so each fluorine atom contains 3 electron pair. So they all 12 is considered. Understood? So the next step is to consider the octet. So boron here is completed this octet, right? Then find the formal charges. Right? So boron got only 3 electrons at the beginning. But look at how it ends the molecule. Okay. So in this one, it has how many electrons? It has 4 electrons of its own. Okay, so if you put dot crosses, you will understand the number of electrons that are kept by boron. So how many electrons it is keeping? 1, 2, 3, 4. But it brought 3 at the beginning, but now it is keeping 4. That means it is the one that keeps the extra electron. Understood? So that means what? In other words, boron is the one that is having the negative charge. Okay, boron is the one having the negative charge. So you can take the form, we call it this as the formal charge also. In another way also, remember, you can get the number of number of valence electrons, and then subtract number of lone pair electrons and subtract half of the bond pair electrons. Let's apply this for boron and see. Okay, so boron had 3 valence electrons, right? And there are no lone pair electrons around that. And it is having 4 bonds, that means 8 electrons. Okay, so 3 minus 4 minus 1, you can take it in by this formula also. So any method you prefer, you are allowed to do, because anyway, they are not giving marks for mentioning the method. They are giving marks only for the final structure. Understood? So I put this dotted and crosses, dots and crosses just to explain the formal charge. Okay, formally showing it. Right, so that is the BF4 minus. So then, right, so anyway, I'll draw the other two also. Right, now take here, chlorine is the central atom. There are 3 oxygen atoms around it. If you take the total electrons, 7 from chlorine, and there are 3 oxygen, 1 oxygen carries 6 electrons, so 6 into 3, 18. And there is a negative charge, that means 1 extra electron. So 26 total electrons. From that 26, we represented 6, no? Then you have 20 electrons. 20 means 10 electron pair. So place that 10 electron pair around oxygen. Then you can put 9, and the remaining pair you have to put the chlorine. Then check octet of chlorine is okay, fine. Then put the charges. Here you have minus, minus, minus. And chlorine will have 1, 2, 3, 4, 5 plus 2 charge. No? Now, since chlorine is in the third period, it is allowed to violate octet. That means it can keep more than 8 electrons in the valence group. So feel free to make more bonds. Okay, so that means you can keep 2 more bonds. So chlorine here. So remember when I'm drawing the double bond, I took from these spaces. If you need, you can take the double bond from the above also. It's your choice. All structures are correct. Okay, so there you have the negative charge. Understood? Then we can go to the final one. Xenon is having 8 electrons. It's a noble gas kind of, right? It's having 8 electrons, and oxygen is having 6 electrons, and 2 chlorine is having 14 electrons. So together you have 28 electrons. You put the central atom, oxygen and 2 chlorine. You have already represented 6 electrons, so 22. That means 11 electron pairs. So place those 11 electron pairs starting from chlorine. You can put 6 electrons pairs for the chlorine and another 3 for the oxygen. That means you have put 9. So 2 will be remaining, place them on the xenon. Then check the charges, you have a minus charge. And 1, 2, 3, 4, 5, 6, 7, you have a plus charge. You can minimize the charges by making more bonds. So finally, the structure will look like this. There are 2 lone pairs around them. Okay, so one of you asked the question, why xenon makes bond? Isn't it a noble gas? So normally noble gases are not making bonds. So take helium, neon, argon, those are not making bonds because they already have a stable configuration and they are very small load. Right? So they are not very likely to make bonds. They don't need to make bonds actually because they're already stable. But take xenon for example. Right? Xenon means in a lower period. This is the reason. Okay? Xenon is in a lower period. That means xenon atomic radius is very high. Okay, so that means xenon valence electrons are located pretty much away from the xenon nucleus. So this radius is higher for xenon. That means these electrons are feeling lesser nuclear attraction, lesser effective nuclear attraction. So that means these are capable of making bonds. Understood? So the reason why xenon makes bonds because it's having higher atomic radius. The valence electrons are less attracted to the nucleus. Okay, so therefore they can make bonds. Understood? So xenon is not trying to become kind of stable, it's kind of making bonds with more electronegative elements. So xenon is only making bonds with oxygen and chlorine. Okay, so that was also an important point. Xenon is making bonds only with oxygen and chlorine. No other elements are making bonds with xenon. You will learn it in a later lesson, but anyway, just from this discussion, you can add it. Right. So, however, these are the structures we have. So, what they're asking is the shape. What they're asking is the shape. Right. So, here you have 4 repulsion units. So, that means it is tetrahedral electron pair geometry, and there are no lone pairs, so tetrahedral shape. Okay. And here you have again 4 repulsion units. Okay. So, that means tetrahedral electron pair geometry, but you have one lone pair. One lone pair. So, that means number. It is trigonal pyramidal electron pair geometry shape. Okay, trigonal pyramidal shape. Trigonal pyramidal shape. This is the shape. And if you take this one, you have 5 repulsion units. So it is trigonal bipyramidal electron pair geometry. If you are having 2 lone pairs, that means it is T shape. T shape. T shape. Okay, so you can see it's actually like a letter T. You click this on 90 degrees, you will get the one we draw in the. Okay, so these are the answers. Let's see how many of you got the correct answer. Tetrahedral, pyramidal, and T shape. Yeah, the numbers. Oh, here is the answer. Tetrahedral, trigonal pyramidal, and T shape. Answer must be answer 4. Let's see how many of you got that one. Okay. Right, good. Right. Now that is the long method. Now you can see it took more time for me to draw these, right? So, but if you try it for the question, for the question that came for the 2024 A level, it will take like 5-6 minutes. You can't take that much time for an MCQ like this. So you have to do it faster. That means, Lamai, we have to develop a faster method, a faster way of drawing the Lewis structure with our practice. Okay, with our practice. So anyway, you have to spend time and draw more Lewis structures now. So with the time, you will be able to draw it fast. So I'll explain how to get the answer for the fourth one. And another thing, Lama, you don't need to draw all the structures. If you check the answers carefully, okay, you can, by only drawing 1 or 2 structure, 2-3 structures, you can eliminate other answers and get the correct one. Okay, that option is also there. Even though there are 4 structures, we are not going to draw all 4. But however, this is an explanation. Okay, in this level, with you, I am drawing all the structures. But let's say you are about to go to the A-level exam. So you are a 2025 A-level student now. So I'm not going to draw all the structures, right? I'm giving you to the point. This is what you should do. Right? But now let's play with the questions and let's draw everything and just for the practice. Okay. Right. So what are the 4 structures they are asking here? IO3 plus NFCl2 F3ClO2 and F4BrO minus. So these are the 4 structures they are given. Right. Now, what is that short method I was telling? Now the thing is this. Now with practice, okay, normally oxygen makes double bond. Normally. So when it makes a single bond, it keeps a negative charge on that. Okay, normally oxygen is not keeping a positive charge, right? So if you take this kind of a molecule, the positive charge usually they are on iodine. Okay, on iodine. So with the practice, you can draw. So now take iodine has 7 valence electrons. From that 7 valence electrons, if oxygen is not carrying any charge, it should make double bonds. Okay, to make double bonds, you need 2 electrons per each oxygen. Okay, what did I say? You need 2 electrons per each oxygen. So here you are having 3 oxygen atoms. That means you need 3 into 2, 6 electrons from iodine. Understood? So you have to subtract 2 into 3, 6 electrons from iodine to make bonds with oxygen. Understand? So then only one will remain. So that one also subtracted because of the positive charge. Okay. These electrons are for oxygen. So that means you will, nothing is left. Understood? So that means around iodine, what do we have? We have a structure like this. We have a structure like this, and iodine is having the positive charge. Understood? So what is the electron pair geometry? And you can see the shape is also the same. Trigonal plane. Trigonal planar shape. So now you can eliminate answers which are not starting with trigonal plane. Right? So there are 3 answers you can eliminate. Answer 2, 3, 4. So then answer must be either 1 or 2. 1 or 2. So then you can see you don't need to draw the second one. Because in answer 1 and 1 and 5 might be the answer. Trigonal plane. Right? In answer 1 and 5, both are having same thing for the second structure. They are telling it is trigonal pyramid. Trigonal pyramid. Trigonal pyramid. So I'm not going to draw that now. Before I finish the discussion on this question, I'll draw it. But let's go to the other one. There's no point of doing it to find the answer. Then think about the next structure. The one they gave for the F3ClO2 is different. In the first answer, it is telling square pyramid. And the fifth answer, it is telling, in the fifth answer, it is telling trigonal bipyramid. So if you draw this structure, you can find the answer. That's what I said at the beginning. Even though there are 4 structures, you don't need to draw all 4 structures to find the answer. Just just check the answers and find the necessary one. Very easy, right? And do. Okay. So central atom is chlorine as usual. There is electronegative atom. You can place the 3 fluorine atoms and 2 oxygen atoms around it. Then you can write something like earlier. So fluorine is having 7 valence electrons. From those 7 electrons, 3 is gone for to make bonds with fluorine. Okay, and another 4. Another form is 2 into 2 because there are 2 oxygen atoms also are gone for the oxygen. So then 7 minus 3 minus 4 is 0. Again, we will not have any lone pairs. That means we'll be having a structure like this. Understood? So what is the electron pair geometry? It is trigonal bipyramid. And shape is also trigonal bipyramid. It's not square pyramid. For it to become square pyramidal, there must be 5 bond pairs and 1 lone pair. So you don't have that one. So what you have here is 5 bond pairs and 0 lone pair. Okay, so that means answer is answer 5. Okay, so let's see how many of you got the yeah, I didn't ask for the answer anyway. I hope you got the 5th answer. Can I see a hand raise who got the 5th answer? Good. Keep practicing, Lama. Okay? Keep practicing. You can be happy about yourself. Right, so here the structure bromine. So fluorine makes single bonds only. Always fluorine makes single bonds only. Okay? And if negative charge is there, usually we keep it on oxygen. That means bromine should have a lone pair. Okay, so check here. You have 5 bond pairs and 1 lone pair. So this is what square pyramidal will be. So that means you can draw around VR, you can draw it in this way. And this is the oxygen atom, the negative charge. And there is a lone pair. Okay. So lone pair and the oxygen atom are perpendicular to the plane. And these 4 fluorine atoms are on the plane. Okay, now about this NF2Cl, we didn't bother about drawing that. Anyway, NF2Cl and there will be a lone pair on this. So it's trigonal pyramid. It's just like ammonia, no? Okay, you can easily find the answer, no worries, right? Okay, good. So tell me the answer you found for the fifth one. So that's some creative question. Actually, they are not teaching you different theories for these sort of questions, like the fifth one. Okay, with MCQ practice, you have to gain the idea. So because all the 4 questions I did up to now, okay, the similar questions we discussed in the theory class, right? But we never did a question like the fifth one. That means you are getting the idea, getting the knowledge. I mean, not the knowledge actually, getting the practice, okay, in a paper too. Okay, so that's why these classes are so important. So don't miss them, right? And keep your reviews with you. Okay, look at the question. Show you the question for a second. Someone is watching the recording, they might not have the paper now. Okay, look at the fifth one. This is the one we are going to do now. And non-transition element X. Element X is non-transition. Okay, non-transition. I'll explain later. And it forms a square plane except4 minus. The shape is square planar shape. Square planar shape. Okay. And what is the common electron configuration of the free X atom in the ground state? Okay, electronic configuration of free X atom in the ground state. Okay, they are asking electronic configuration. Electronic configuration. So that's what they are asking. Okay. Now, there are few things we need to understand. Right. What is meant by non-transition? Non-transition means it can be either in S block or P block. Okay, so for this unit, you have to take like this. Okay, so when we discuss the unit 6, okay, this what I said will be a little bit different. Going to change a little bit, but no point of telling it now. So therefore, for questions like this, just say non-transition implies that, okay, this whatever the X molecule belong to either S block or P block. So anyway, S block elements are not making these sort of bonds, covalent bonds. You understand? Only beryllium makes BeCl2. That's it, right? Others are not that much making covalent bonds. So it suggests you, okay, so it is there in the P block. Understand? It is there in the P block. That's so the all configurations given also the P block configuration. So actually this point is not useful for us. Not useful. Because when you check the answers, you can anyway, the only the P block element value, right? Okay. Right now take this pair planar thing. You know, always fluorine makes single bonds. Always fluorine makes single bond. Single bond. And it keep no charge. And keep no charge. So that's as a fact you know that now because you draw several structures with you. So did you see any structure? Fluorine is having a charge or having double bonds? No. Fluorine always make single bonds and it keeps six electrons, or you can say 3 lone pairs around there. Always. It's a must thing. Okay. Now, this negative charge must be there on where? On the X atom. Okay. And if it is to be square planar, you can again understand how many lone pairs and how many bond pairs will be there. There should be 4 bond pairs and 2 lone pairs. That's how it becomes square plane. 4 bond pairs and 2 lone pairs. So that means around X1, you have to have 2 lone pairs. Understood? That's how it became square plane. So if you want to represent it properly or nicely, you can go like this. The 2 lone pairs. These are the fluorine atoms and Here you have the negative. Understood? Hmm? Right. Right. So how do we decide the group now? So now you can do think and get the answer. But as a review, to write in a review, I'll give you a proper method. Do you remember the formula we used to find formal charge? Formal charge. I wrote that one in the board 2 minutes ago. Right? Formal charge of a given atom is equal to number of valence electrons minus number of lone pair electrons and minus half of the number of bond pair electrons. That is the formula. Remember? So now applying. Okay. Number of as the formal charge here is -1. Valence electrons we don't know. If you know the valence electron, you can decide the group or you can decide the configuration. Right? Let's say you have 3 valence electrons. That means configuration is NH2 and P1. So then you can think, no? Understood? So let's find out this X. So number of lone pair electrons, you have 4. And half of the bond pair electrons, half. You have 8 bond pair electrons, so half of that is 4. So -1 equals x minus 4 minus 4 minus 3. Okay. -1 equals x minus 8. So x is equal to what? +7. So which group it belongs to? 7 valence electrons means NH2 NP5. Group 17. Group 17 in the periodic table. Understood? So then your answer is answer 5. Okay, I saw some of you had taken the correct answer. Okay, very good. Answer is answer 5. Good. Right, so that is how you get the answer for the fifth one. Fifth one. Right. Then the next question. Question number 6. So this is the last week topic. I promised you to put a question on, theory facts from hybridization. So this is that question. So tell me what is your answer, everyone? Read to the group. What is the incorrect statement? Yeah. Okay, very good. So answer is answer 5 for the hybridization question. It's asking the incorrect one. So I'll tell you why the fifth one is incorrect. Hmm? Why the fifth one is incorrect? Look at that. It is telling a hybrid orbital in a particular atom can overlap with hybrid orbital or unhybridized orbital, atomic orbital of another atom to form sigma or pi bond. And this is the wrong part. It doesn't make pi bond. Understand? Hybrid orbitals are not making pi bond. They cannot make pi bond. Understood now? They cannot make pi bond. They only make sigma bond. They only make sigma bonds. They can make sigma bonds with another hybrid orbital, or they can make sigma bonds with atomic orbitals. No problem with that. Okay, but they don't make pi bonds. Why? Why they can't make pi bonds? Because hybrid orbital is something like this one, so they can't laterally overlap. Okay, so then there is nothing here, then it's not going to happen. What is laterally overlapping? Our p orbital, like this they overlap. They make a good bond. Understood? So only pi bonds are made by p orbitals and sometimes by d orbitals. Okay, p and d orbitals are the ones who are capable of making pi bonds. Nothing more. Understood? Hybrid orbitals can't do that. Hybrid orbitals are making only sigma bonds. Let's say it can make sigma bonds with s orbital. It can make sigma bonds with another hybrid orbital. It can make a sigma bond with a p orbital. Okay, can happen. Can happen. Understood, but they all are linear overlapping. So they overlap along the internuclear axis. They are not pi. Understood? That's why the fifth one is wrong. I hope you all understood that. So some of you said the second one. Let's read that statement. The number of hybrid orbitals formed is equal to the number of atomic orbitals. Yeah, that is true. If it is sp3 hybridization, you have four hybrid orbitals, and s, and there are p, s and 3p orbitals, right? So they mix together to form four equal orbitals. That is the spin. You have four sp3 orbitals. So I hope you remember the story I told you in the class. I'm going to tell it here, right? So what is the purpose of being hybridized? Okay, they need to be hybridized in order to explain the electron pair geometry and shape, no? Right? Okay, so we have to learn another very important topic, resonance. In the next paper, I'm going to explain you and do questions with you about this resonance also, right? Okay, so it's about the sixth question. Answer is answer 5. So I think other statements I don't need to explain anything. But go to the first one and see. The concept of hybridization cannot used for an atom alone. It is used to describe the bonding form in a particular molecule or ion. Yeah, that is true actually. Why? Because when atoms are not making bonds, they no need to be hybridized. No? They can just stay as they are. So we don't have to worry about the hybridization when we can't explain the electron pair geometry and shape with the available at more orbitals. That's why we need to hybridize all the orbitals. Then we can explain electron pair geometry. Then we can explain why CH4 is tetrahedral. Understand? Because in the s orbitals and p orbitals are different lengths and different sizes of shapes. They can't make equal bonds. Therefore, they must undergo hybridization. So that problem comes to us when carbon make bonds. Understand? So when carbon doesn't make bonds, no need to consider the hybridization. Okay. Right. So therefore, first one is correct. Second one is also correct. I explained. Third one, there should be minimum 2 atomic orbitals. That is also true. At least the smallest hybridization is sp. There you have different orbitals, right? Because same orbitals are not going to mix anyway. So at the point of mixing, anyway they are equal. Yeah, yeah. Anyway, even though the s and p orbitals are in different energies, but the hybrid orbitals are at the same energy. And the energy will be something in between the s orbital and p orbital energies. Okay. Yeah. Seventh question. Yeah, tell me what is the answer first of all. It's very ancient question. 1999. 1999. What is the answer you selected for that? It's about BF3 and NCH3 twice. Will anyone get an answer for this one? So here, this is a very good example for dative covalent bond. Okay, dative covalent bond. Let's see. Answer, yeah. So there are two answers. I mean, it's a ABCD question, there might be two answers. Let's see. So here you have the N, there is a lone pair on nitrogen, and this one is electron deficit. Electron deficit. So they make a bond. You can say the nitrogen is donating the electron pair to the boron, and then they make a bond. Or you can think in this way also. And I draw it in the red color. Okay. So you can assume that this one is giving one electron to boron, right? And then they would become like this, no? One electron here and boron also 1 electron here. Then they can put their electrons and make a bond. You can think in that way also. So that's how we explain the dative covalent bond. And there are two theories to explain that. So let's read the answers and understand what is correct. It could be assumed that initially an electron is temporarily transferred from nitrogen to boron atom. Yeah, that is what I said. So according to that concept, the red color one, A is correct. A is correct. Okay. So then electrons are not transferring from boron. So B is wrong. Look at C and D. Boron doesn't supply the electron pair, but nitrogen supply the electron pair. So D is also correct according to the blue color. So answer is A and D. A, D correct means answer 4. So it's a good question about dative covalent bond. Dative covalent bond. So remember, this is an dative covalent bond. Dative covalent bond, or we can say coordinate coordinate. And then you can draw the structure in this way also. Here you can say it is negative and positive also, because once it donates the electron, it becomes positive. This way also a good one to represent dative covalent bond. Okay, so there are two ways that a bond can be formed. Okay, so one way is having single electron, they can overlap and make the bond. And the other way is uh, an orbital that keeps two electrons and with an orbital without any electron. Then also they can overlap in the similar way. These are the only two ways that a bond can form. A covalent bond can form. Okay, because the orbitals with 2 electrons and 1 electron, they are not going to overlap. Orbitals with 2 electrons and other orbital with 2 electrons are not going to overlap because there is too much repulsion. Too much repulsion, so no overlap. Too much repulsion, so no overlap. Understood now? So that's the story. That's the story. Seventh one, answer is answer. Right. So now those are the questions about bonding. Those are the questions about bonding. Tell me what is the answer you selected for the 8? Answer you selected for the 8. Ah, yeah. So one of you are asking about this CH3 and yeah. Okay. This one, you can write it in this way also. No issue, because why? You can write it in this way also, right? No problem. No problem, but it is good to write like this. Why? Because nitrogen is anyway making the bond with carbon. So in that case, it's better to write carbon bonded to the nitrogen. That is a better way, okay? You can write it in this way also. This is also not wrong, but if possible, we should try to show the actual atom that is bonded with nitrogen. That's a good thing to do. That's all, okay? There's no reason, no other reason. Right, so any other doubts you have? You might have a doubt again with the CH3 thing. Anyway, Lamai, don't worry about that one now. Okay? Just consider they have put CH3 and bracket 3. That means CH3 treat it as a single atom. Okay, so just for your understanding, think it is as hydrogen. Replace this one by hydrogen and consider this molecule as NH3, NH3 and BF. That is better for you. Okay, because you are not studied about organic chemistry. So therefore, you might have doubts about the CH3. I just ignore it. Consider it as some other element, hydrogen. Will make you think it easy. Okay. Anyway, we'll be learning it soon. Don't worry. So what is the answer for the eighth one? So I saw several answers. Answer is answer 4. Now let's explain that one. Question number 8. It's asking what is the false one. What's the false one? First of all, I'll explain the answer. Let's write why the fourth point is wrong. Fourth statement is wrong. It is telling 2L plus 1 gives the number of sub-energy levels in a principal energy level. Now, it is giving you 2L plus 1 gives you total number of orbitals. Number of orbitals in the given sub-energy level. So it is giving you the total number of orbitals. Let's say L is equal to 0. That means 2 times 0 plus 1 is 1. Okay, that means you have only one s orbital. One s orbital. One s orbital. So let's say L is equal to 1. That means 2 times 1 plus 1, 3. You have how many orbitals? 3 orbitals. Like that, it is telling you the number of orbitals, not the sub-energy level. So what is representing sub-energy level? Okay, so I earlier class I explained that one. So anyway, sub-energy levels are represented by n. N, the number for the energy level. So let's say if it is first energy level, one sub-energy. If there are two, the energy level is 2, then there are 2 sub-energy levels, S and P, 2s, 2p, like that. Okay, represented by n. So then electrons are represented by 2n square. Orbitals, total orbitals in an energy level is represented by n square. Like that. Remember those. Okay, so if the n is according to the principal quantum number n, you can get the number of orbitals, sub-energy levels, and electrons also. Right? And here it is representing orbital. That's why fourth one is wrong. So that means the other statements are correct. So write a good review on them. Why those are correct? For example, I quickly tell chromium, it is telling 7 electrons azimuthal quantum number L equals 0. L equals 0 means S. If you write the chromium configuration, 3d5 4s1, ground state configuration. See how many electrons are there? 2, 2, 2, and there are 6 and 7. 7 electrons. That's true. Okay, that's true. So then take the next one. 3 orbitals with quantum number n equal 3, L equal 1. N equal 3, L equal 1 means lamai. That is 3p. 3p you have anyway, if it is p sub-energy level, you have 3 orbitals which can contain 6 electrons. That's true. An electron with the quantum number at 200 plus half should reside in the 2s sub-energy level. Yeah, it is. The first two quantum numbers are representing the sub-energy level, 2s. 7 is also correct. Let's see the fifth one. Okay, calcium has 4 electrons with magnetic quantum number Mn plus 1. Write the configuration of calcium and understand. 3s2, 3p6, and 4s2. So calcium is having only 4 and S and P electrons, right? So S electrons are not having Ml plus 1. Ml plus 1 you can find in the P sub-energy level, D sub-energy level, like plus 1. So that means out of 6 P electrons, 2 are satisfying our condition. So that means you have 4 electrons. So that is statement is also correct. Understand? So it's also a good question. And tell me the answer for the question number 9. What is the answer you got? What is the answer you got for the question number 9? Look at the statement. The wavelength of electromagnetic wave relevant to the electron transition from 6 to 3 is greater than transition from 4 to 2 in H emission spectrum. N equal 1, 2, 3, 4, and 5. We need one more, no? Let's say this is n equals 6. So 6 to 3. 6 to 3, this is the transition. 6 to 3. And 4 to 2. 4 to 2. Okay. 4 to 2 transition is longer. And it is in the Balmer series. Balmer series in the visible region. Visible region, actually, what is the color for the 4 to 2 transition? If it is from 3 to 2, red. 4 to 2, green. Green color. But this transitions that are ending with energy level, post energy level, those are belong to the infrared region. And if they are coming to third energy level, that is Paschen series. Paschen series is in the infrared region. So it's having low energy. Okay, so low energy. So think from there. So this one is having low energy. This one is having high energy, relatively high energy. So if the energy is higher, then its wavelength is lower. Okay, because you know energy hc over lambda with a photon, you can remind this equation. And you can see that if energy is higher, wavelength is lower. Then the Paschen series lines will have a higher wavelength. So that telling the wavelength of 6 to 3 is greater, that is correct. A is 2. Now look at B. Electrical field, then electrical field alpha shows a greater deflection. No, those are very basic facts. Even in the revision class, I started on that yesterday. In the newcomers, I discussed that. So alpha rays are not having the largest angle because if you pass alpha, beta, and gamma, gamma is traveling without any deflection. Alpha, if you put a positive field, okay, this is positive and this is negative. So gamma is bending, but it is not that much bend. Sorry, alpha is bending, but it is not that large angle. But beta is showing a considerable angle, a large angle. Because why? Beta is a very low mass particle. It's electron, but alpha is having a very low deflection angle because it is a very heavy particle. Understood? So therefore, B is wrong. What about C? Atomic radius of oxygen is greater than ionic radius of F minus. So that is also wrong. Okay. So about radius, we studied several important points. In that one point, remember, you learned that nitrogen, you learned that the anions are having larger radii than the same parent atoms. Even F minus is larger than nitrogen. As a fact, you remember this. Okay, so same thing goes there for the cations also. Sodium, magnesium, aluminium, and sodium plus is smaller than aluminum. Remember that one's a good thing to keep in mind. Okay, the C is wrong. Understood? And then what about the D? The spinning of maximum available unpaired electron of P sub energy level to the same direction causes the configuration for the low energy. D is correct because low energy means okay high stability. Then according to remember whose role? According to Hunt's rule, we know if there are 3 electrons in the P sub energy level, they should still say, oh, I give 1 or 2, let's say, they should be there having the spin to the same direction. So then it is stable. Understood? It is stable. So answer is answer A and D. A and D are correct. Okay, so that means answer 4. Answer 4. Understood, Lamai? Right. So let's go to the 10th question. I'm going to stop from the 10th question. The structured question, I'll add the answers to the group. Okay, you can check it. I know we did several structured in the class also, so it won't be a problem. Anyway, let's properly discuss the 10th question. Go to that one and see. I added the structured essay question here, 2019, just to remind you the theory. Anyway, so what is the answer for the 10th one? Which of the following are correct orders about the size, affinity, ZDFF? Okay, B plus is smaller than the parent atom. So cations are smaller than the parent atom and anions are larger than the parent atom. So the one about the atomic or ionic radius, the first one is correct. Okay, because here you have more nuclear charge, more nuclear attraction. Here you have electron repulsion, more electron repulsion. Okay, here more, or you can say less electron repulsion, that is better. The size is lower. Then take B, the electron affinity, neon, phosphorus, chlorine, and sulfur. Okay, electron affinity. Electron affinity is lower for neon. The affinity is low because they already have a stable configuration, MS2 NP6. So very low affinity, stable. And phosphorus also having a stable configuration, no? You know, MS2 NP3. It is kind of like electron, but not like the other elements, right? So anyway, it is also having a lower affinity, but this question becomes wrong because of this. Understand why? Because I said at the theory class, okay, so in a given period, highest electron affinity is shown by group 17 element. Because why? It is the smaller one, okay, smaller one with good nuclear attraction, right? So in each period, let's say in the second period, chlorine is the highest electron affinity. Third period, chlorine is the highest electron affinity, like that. So Cl obviously will have a higher electron affinity than sulfur, which is in the same period, right? So B is wrong. B is wrong. Then look at C. ZDF. What is ZDF? Effective nuclear charge. Okay. Z minus sigma, nuclear charge minus shielding it. So they all are oxygen atoms, ions. Okay. So that means Z same. So they only have variable shielding effect. So shielding effect increase with number of electrons. So this one is having O2 minus is having more shielding effect. So it should have a lower ZDF. So that C is also then correct. ZDF is higher for the O plus. Okay, so if A and C are correct, then the answer will be obviously answer higher. Okay, but anyway, let's look at the D also. Yeah, that is correct, no? I wrote that one only. So then A, C, D are correct. A, C, D are correct. Answer is answer. Okay, students, understood that one? Any doubts regarding that? A, C, D are correct. Okay, very good, very good. Good. Most of you got the answer. Nice. Right, good. Okay, that's all. I'll give you the paper 13 also in our next class. Right, so it will contain. I already have prepared the paper, so I at the printout also. I add in the board paper. So anyway, we'll have this one. There you have a very nice structured essay question. Surely I'm going to discuss that next day. Because for the paper 13, I put only 5 MCQ. Then because I want to save some time to discuss the 2018 structured essay question. So in my book, the one I gave you have 2019 to 24 structured essay question. Those are the new syllabus. So 2018 is the old syllabus one, but it's a good question. So we have to discuss properly in a paper class like this. So you can refer the recording later. Okay, right. So good night, students. Study well. If you have further doubts, you can send a message or ask them in the class. Okay.